Section 3 of Chapter 16 is about equilibria involving complex ions. We talked a little bit about complex ions in Chapter 14. We looked at the hydrated aluminum ion and how it was a weak acid. So let's talk a little bit more about what complex ions are. They are ions, so overall they will carry a charge. We're going to see a metal ion in there, and it's going to be surrounded by what we call ligands. Now these are molecules or ions that have lone pairs of electrons, and these lone pairs are donated to an empty orbital on the metal ion, and then a covalent bond is formed. So some common examples are given here for your ligands. And if you take water, for example, we've got a couple of lone pairs, and a lone pair then would be donated to an empty orbital on a metal ion. Here you see some examples of some complex ions. Notice quite a few of them have water in them. And notice how they have an overall charge because they are ions. The metal ion can have a different number of ligands attached, and when we count the number of ligands that are attached to the metal ion, we call that the coordination number. The most common coordination numbers are 6, 4, and 2, and you can see with this cobalt complex ion here, this would have a coordination number of 4. We've got COCl4. So 4 chloride ions attached to our central cobalt metal ion. Notice the overall charge on the ion is -2. Cobalt has a +2 charge, and then if you add 4 chlorides, which have a -1 charge, overall that's where we get the -2 charge. When a complex ion is formed, the ligands are added one at a time to the metal ion. Each time a ligand is added, there will be a new equilibrium constant associated with that. That's called the formation or stability constant, but it is, again, just an equilibrium constant. Here you can see the formation of a complex ion between beryllium and fluorine. There are 4 steps, each with its own equilibrium constant, and the product in one step is the reactant in the next step as another fluorine is added. The overall reaction is written here where we have the beryllium ion and the 4 fluoride ions combined together to give us our complex ion. If you wanted an equilibrium constant for the overall reaction, you would take the product of all of the formation constants. Now let's talk about complex ions and solubility. If we have a water-insoluble ionic solid, say something like silver chloride, generally there are 2 strategies for trying to dissolve it. If your anion is a good base. Now, chloride is not a good base, but if it was, then we could increase the solubility by making the solution acidic. However, in this case, the anion is not a good base, so the chloride ion is not going to combine with hydrogen ion to make hydrochloric acid. We can get the solid to dissolve, the silver chloride to dissolve, if we add a ligand and form some complex ions with the cation, in this case the silver. So here's our silver chloride. The KSP is very small. This is not very soluble. However, if we add some ammonia, that's going to be our ligand, we are going to be able to pull some of the silver ion out of solution, forming this complex ion. According to Le Chatelier's principle, if we remove silver ion, the reaction will shift right, and then that's increasing your solubility. We're getting more silver chloride to go into solution. This is the overall reaction. And if you needed an equilibrium constant for this overall reaction, we would take the product of the three equilibrium constants that are given there. If we know the equilibrium constant, we can then solve for the solubility of silver chloride using the equilibrium expression. And we would find that our solubility is greater in this basic solution with ammonia than silver chloride alone, just in water.